Hi everybody. So this is my second video on modelling real-life problems with the volume of a revolution. In this example, we're told that the diagram shows a timer, and the shape of the timer is modelled as a solid of revolution of a curve, c, about the y-axis, and the curve has the equation y equals x cubed, which is this equation here. Sand flows through the timer at a rate of 8 centimeters cubed per minute, and the designer wants the timer to empty in 6 minutes. We've been asked to calculate to one decimal place the height of the sand that should be placed in the top half of the timer, and then to state a limitation of this model. So because we're going to revolve around the y-axis, we're going to use the equation where the volume will equal pi times the integral between the range of a to b of x squared dy. So the first thing we need to think about is making x squared the subject of this equation. So if y equals x cubed, then we can raise both sides to a power of 1/3, so y to the 1/3 will equal x. And then we can square both sides, so x squared will equal y to the power of 2/3. And then we can substitute this into our equation. We know our limits are starting from the x-axis, so a will be 0, and b is the value we're trying to find. So we'll say the volume will be pi integrated between the limits of 0 and, let's say, a is what we're trying to find, of y to the 2/3 dy. And we're told here that sand flows through the timer at a rate of 8 centimeters cubed per minute, and the designer wants the timer to be empty in 6 minutes. So the volume of the sand will be 6 multiplied by 8 centimeters cubed per minute, and this will give us a volume of 48 centimeters cubed. So we can replace this v with 48. So now all we need to do is integrate this y to the 2/3. So 48 will be equal to pi. We'll add 1 to this power and we get y to the 5/3. We'll divide by the new power and we'll have our limits of 0 to a. Now dividing by 5/3 is exactly the same as multiplying by 3/5. So we'll have 3/5 of y to the 5/3 between our limits 0 to a. So now I can simplify this by moving this 3/5 out in front of our bracket. So the volume will be equal to 3/5 times pi multiplied by y to the 5/3 between the limits of a to 0. We can now substitute in our limits, and when I substitute in 0, we get 0. So the volume will be equal to 3/5 of pi multiplied by a to the 5/3. And now I can divide both sides by this 3/5 pi. So we get 80 over pi will equal a to the 5/3. I can move this 5/3 to the left-hand side. So a will equal 80 over pi to the power of 3/5. And when I work this out, we get a will equal 6.98 centimeters. Okay? For part B, state one limitation of this model. Well, we could say that the flow is unlikely to remain constant. We could also say that the timer is unlikely to be perfectly smooth. Okay?